So we have this question on dimensional analysis, and it is given that the speed of sound v in a medium is proportional to or is dependent upon is proportional to the modulus of volume elasticity E, and I'll take the power as A. Let me just rewrite this again. So this is proportional to E raised to the power A, and density of the mediums, density raised to the power B. So we have this relationship, and we are expected to find out the values of A and B over here. So this will give me V equal to some constant K E raised to the power A and rho raised to the power B. And this is V. Now let us look at the dimensional equation for all these terms V, E and rho. V we know is velocity, so we will have its length upon time. The unit is meters per second, so we will have m raised to the power 0, L raised to power 1 and T raised to minus 1 length per time. So this is the dimensional formula for velocity. What about E? E is modulus of elasticity, modulus of volume elasticity, and we know that E is, if it is modulus of volume velocity, it is given by pressure divided by change in volume per unit volume, which is basically bulk modulus of elasticity. And if you look at this equation, this denominator is ratio of volume, so it will not have any unit, and therefore E will have the unit of pressure. So what is the unit of pressure, or what are the dimensions for pressure? So pressure is force upon area, force upon area. Force is kg meter per second, kg meter per second square, that is force, and we again have area over here, so this will be meter square. So finally what I get over here is kg per second square meter, and therefore E will have the dimensional formula as kg, so m raised to the power 1, L raised to the power minus 1 and T raised to the power minus 2. What about density? Density, we know the unit is kg per meter cube, and so this will be m raised to the power 1, L raised to the power minus 3 and T raised to the power 0. There is no dimension of T over here. So I'll now put these dimensions in this particular equation. Let me call this equation 1. So I'll put these dimensions in equation 1. The dimension of velocity is m raised to the power 0, L raised to the power 1, T raised to the power minus 1 is equal to some constant k and its unit. And the dimensions of E we have found out is r m raised to 1, L raised to minus 1, T raised to minus 2, all raised to the power a. And density is m raised to the power 1, L raised to the power minus 3, T raised to the power 0 and raised to b. And now let us compare the powers of m. The power of m on the left hand side is 0, and on the numerator, on the right hand side, is this is 1 and this is a, so this is equal to a plus the power of m over here is 1 into b, so a plus b. So this is 1. Let's compare the power of length. So I get 1 equal to, this is minus 1 and there is a power here a, so minus a, and this is minus 3b. Let us compare the power of t. So minus 1 equal to, this is minus 2a, and the power of t here is 0, so we will have 0 over here, so minus 2a. So I got these three equations, and with the help of these equations I can find out values of a and b. Obviously from here I get 1 equal to 2a, and therefore a equal to 1 upon 2. And if I use this equation over here, 0 is equal to a is 1 upon 2 plus b, therefore I get b equal to minus half. So I have obtained values of a and b. B is this, a is this, and I can go back to equation 1 and rewrite equation 1 as v is equal to some constant k e raised to the power a is half and rho raised to minus half, and therefore this could be written as e raised to half by rho raised to half. And therefore finally I can write this equation as v is equal to some constant k square root of e raised to the power half, or sorry, just e and rho, and this is what is the final equation we obtain. So v is equal to k e upon rho. So we have got a relationship between v and e and rho, and the value of this constant can be obtained by experiments. This is how dimensional analysis helps us to obtain a relationship between v, e and rho. Thank you.